Let's see how we can generate a square function using the Fourier series approximation on our CPU. Now I have drawn here a little square function, and you can see the perfect function in white here. So that's what we're aiming towards. But we're going to generate an approximation to this using the Fourier series. So you can see the approximation I've generated in blue, and we have this curve here, which we can see is tending towards this square function. Now we've used three terms in order to generate this. So here are the three terms here: 4 upon pi sine x, 4 upon 3 pi sine 3x, and 4 upon 5 pi sine 5x. Now what we can do is we can divide these numbers out. So 4 divided by pi will give us this number here, and the 4 upon 3 pi is this one, and the 4 upon 5 pi is this one here. So we have to generate this little polynomial with three terms within our assembly language. So let's go ahead and we'll see how I've generated this in our assembly language. This is a subroutine which will generate our Fourier series approximation to our square function. So you can see here I made a little note of the three terms and also the polynomial which we will be using within the code. Now I'm not going to talk through all of this code in detail. I will produce another video about this, and I will load it into the Design a CPU 3 course, and it will have a lot more detail in it. So, but you can see here quite clearly that it's going to be broken into three parts. We're going to generate this part here using this code, and then this part here with the code below, and finally this part. And we will add them all together and we'll get the final output, which will be the Fourier series approximation to a square wave using these three terms. Now, in order to generate the actual square wave, we're going to pass in the values from 0 to 2 pi. So that in effect is going to go through 360 degrees, and we're going to go through that 0.1 radians at a time. So you can see here we've got the input here is going to be the value of x, and it starts at 0, then 0.1, 0.2, 0.3, and it goes all the way up to 6.3. So we're going to pass all of these values into our subroutine, and we'll call our subroutine Fourier. So this is the subroutine here. Okay, so we pass all the values into that subroutine, and it returns those values to the addresses Fourier underscore x. Now I've gone ahead and I've loaded this program into the machine, and I have ran the program. The program took about 4 hours or so to run through all of the 65, I think there is 65 values. So there's no point in me sitting showing you this running because it just runs too slowly. So what I'll do is I took all of the values that we got from the output of the program, which is saved into the RAM, and I've copied them onto an Excel spreadsheet. So let's have a look at that spreadsheet now. Now, after the program ran on the machine, I copied out all of the values for the answers, which were in our 8.8 fixed point, and then I converted them into decimal. So you can see here that on the first column here, we've got the input in radians, so it goes from 0, 0.1, 0.2, 0.3, all the way up to 6.3 radians. And the next column gives us the actual output from our simulation on the CPU. So this is the CPU output for each of those. Okay. Now the next column here gives us the result that we expect to get, and we get these values here from the graphical calculator, and you'll see that in a moment whenever we get and have a look at the two values side by side. So I've taken one away from the other, and you can see the difference here. Okay, now from this we can see that the results are and approximately 2 decimal places of accuracy. So some of them are maybe 1 decimal place, but most of them are accurate to 2 decimal places. So you can't see much from these values here. What we want to do is take all of the points and load them into the graphical calculator and make a comparison. So let's do that now. We have our square wave approximation here in blue, and you can see if we zoom in that I've actually generated the points that we expect to get. So I've put in each of these points, which are going to be spaced out by 0.1 radians. So this is the first one here. We expect to get the answer 0.375, and then at 0.2 we expect to get 0.707, and then we get 0.3, and so on and so forth. So we can make a list of all of the values that we expect to get from this Fourier series approximation. Now let me superimpose the results we actually get from our CPU. I have superimposed the values that we get whenever we run through the simulation on our CPU. So you can see the values here are in yellow, and they do approximate to the square function. So I'm quite pleased at the accuracy of these results. Let's go in and we'll have a look at just a few of them. Now I'm not going to go through the values in any detail, we want to just have a quick look and see them. So here's the first one here, we expect to get 0.3746. The value we actually get is 0.359. And you can see here the values are really quite close. It only goes off at a couple of points, but again it doesn't go off by very much. So let's take this one up here. We expect 1.1229 and we get 1.113. So most of the values here for our simulation are within 2 decimal places. There's some of them within 1 decimal place, but in general we have a really nice approximation to our square function using the simulated values from our CPU. So I'm really quite pleased at this, considering that if we were going to be using the 8.8 fixed point system, it's going to have an accuracy of approximately 2 decimal places. So it means that we're not generating any more errors through our code. So there's no any systematic errors running through the code. It's all working really quite cool. So very pleased, very happy at this. So thank you for listening. I'll get you on the next video. Goodbye.